we'll move to the practical aspect. So, introduction to survival analysis. So the first thing there, we are going to import the data we are going to be using for survival analysis. So we are going to be importing the data. So if you have your data on, the data I'm going to be importing is a CXV file. I mean, it's an XLX file. If R cannot read XLS file directly, so you have to install a particular library, a particular package known as readxl. So without installing that library, without installing that readxl, you can't read files that are XLX. R can read files that are XLS. If your file is in CSV, just press read.csv, then you write the name of the file and it's going to bring the file to you. So, but R can read XLS files directly, so you have to install that library. So first of all, I already have that library in the system. So you have, I'll just run it. So I have, sorry. So I have run that line of code. So I'm going to import my data. I don't want to be writing, so I will just name the data to be Y. So you can use this equals to as an assignment operator in R, or you can use the this sign as assignment operator in R. But I would prefer to use the equals to sign because I'm used to the equals to sign. So I will be using the equals to sign as a assignment in R. So the name of my data is projects. So that's the name of my data. So I'm going to import my data. So my data is, I have imported my data into R. So if I call that data, if I go to my global environment, then just look at what my data looks like. So you can see this is how my data looks like. I have the patient ID. This is data on breast cancer patient. It was collected online. So this is, you can see we have the patient's ID, we have age, which is continuous, we have gender, which is categorical, we have protein 1, protein 2, all these are continuous variable. So we have tumor stage, which is a categorical variable. We have histology, which is also a categorical variable, and so on. So we have status, HR status coming. So we have the surgery type and date of surgery. We have date of last visit, the status of the patient, whether the patient is dead or alive. We have the survival days, the gender status, HR status, and so on. So that is so let's move back to our data. So then we have to draw the first thing we are going to do is to draw the Kaplan-Meier curve. So before drawing the Kaplan-Meier curve, we have to install a library, a package known as Survivor. I have the package already installed on my system, so I'm just going to call for the library. So I have called for that library and the library called Survivor. So we are going to, first of all, draw the Kaplan-Meier curve. So to draw the Kaplan-Meier curve, I will name it to be Km. Let me name it to be Km. So equals to, so this is the function, the code to write your Kaplan-Meier curve, which is this Km equals to solve fits. This is a sub function. This sub fit is a function inside the survivor, and this solve is a sub function of this solve fit. So you have to put your survivor time there and the status. From this part, from our data, our survivor time is the date of surgery to our last visit. So that's what I used as the survivor time, and the status, what we are interested in is either the patient is alive or dead at the end of our study. So the data is claimed already. So the survivor days, I converted the days between the surgery, date of surgery to the date of last visits, which is what from this 2017 2017 so to 06 2017 19. So the survival days between the date of surgery and date of last visit is shown in that column there, and the status is if the patient is alive, it is 0, and if the patient is dead, it is 1. So status 2, we are going to be using status 2. So if the patient is alive, it is 0, and when the patient is dead, it is 1. If the patient is alive, it is 0, and when the patient is dead, it is 1. So those are our survival time and our status respectively. Survival days is the survival time, and our status is status 2. So status 2 is our status. So this tilde sign is just to show that you are drawing your Kaplan-Meier curve without considering any covariates. That you are drawing your Kaplan-Meier curve without considering any covariate, without considering anything, like you are not considering the histology, you are not considering HRL status, you are not considering the stage of the cancer. So this is just the survival days and the status alone. You are not considering any factor. So to just run that. So you can just print out to show you, print KM. So it's going to print this. So our numbers of observation in our data is what? 313. And we have 24 variables in that particular data set. And here, if you look at the console, you see n number of events, which is 313. The events, or this event is our what? Event of interest, which is 61. That means 61 patients died in the particular, in this study. 61 patients died in this particular study. And this median 1455. It means that the time at which 50% of the population dies, that means 50% of the population, that half of the population died at 1455 days. So this is the number of days the population died, and you see the lower 95% confidence interval is 917, and the upper 95% confidence interval is not available. So we can also draw a life table. Life table. I'm sorry I did not put life table at the slides. Life table, it defines the mortality experience of a particular group of people or a particular cohort of people. So life table is also a useful tool in studying survival analysis. So let's draw the life table. So we just have to use summary of KM. So this is our life table. This is the life table of the particular event we are studying. So you can see time at time 0, that is at 0 day. Number of patients that is the total. Everybody is at risk of dying at time 0, at a particular day 0. Everybody is at risk of dying. So that day, numbers of people that experience that event on the first day, that is 0 day, that immediately after the surgery, numbers of people that died is 1. So at day 0, that's what this N event is talking about. And this survivor is the probability of a patient surviving at the 0 day, day 0. That is what this survivor is telling us about. And this is the standard error. And this is the lower 95% confidence interval and the upper 95% confidence interval. If you move on also, you see at day 10 also, 1 person died. So between day 0 and day 9, 1 person also died. Between the 9th day and the 10th day, 1 person died. So that's how it's going to be bringing. We can now draw the Kaplan-Meier curve. So we can just plot Km. So you can see this is the curve at our right hand side. So this is the Kaplan-Meier curve. You can see at day 0, there is 100% survival of patient at a particular day 0. We have 100% survival of patients. So as we move further, you see at day 1000, this 1000, the 1000 day, you see that like 0.5, 0.5 something, 57 something patients, the probability of surviving that at the 1000 is 0.575. So if you look at this particular graph, this curve is not that appealing. It is not that appealing. It's not that beautiful in sight. So we have to make use of the GG plots that to make it more beautiful, to make it more appealing to the eyes. So, and the GG plot or in Survivor is embedded in this library that I'm going to run. This is the Minor library. So I've installed this library already in my system. So I'm just going to run it. I call for the library. So I load this particular package. You see, it has loaded ggplot2 and ggpulr. To make this plot more appealing, so we use this ggsoft plots in this Minor library. So sorry about that fit. So we want to draw the GG plot for this particular Kaplan-Meier curve. So, and we have named this Kaplan-Meier curve to be Km. The data is what? We are getting our data from Y. I've named our entire data to be Y. So that's why our data is equals to Y. The risk table, risk table is not risk table is not compulsory in the code, but I will just make it true so that you can see what a risk table looks like. So that T is true. So the confidence interval, the confidence interval is this line, these two lines that are there. This line, this upper line and this lower line is the confidence interval. If I don't want it to show, I can just put false, and if I want it to show, I could just make it to be true. Let's make it to be true. So, and let's run this. You can see, so it's running. So this is, you can see it has changed. It is more appealing to the eyes now using this GG plots package. And you can see the risk table down here. Let me zoom. So this is how the graph looks like. You can see the risk table below. The risk table is telling you the numbers at risk, and so the risk table is telling us the numbers at risk, which is what? 313. For all at 15, the numbers of this is the numbers at risk, and at time 0 we have 313 that are at risk. At time 1000 days we have 15 people at risk. At time 2000 days we have what? 3 people at risk, and at time 3000 days we have 1 person at risk. So that is what this one is telling us about. And to draw the Kaplan-Meier curve for when we want to consider a covariate, we are considering a covariate. Let's consider from our data, let's consider the cancer stage or the tumor stage. So we can just copy this code and just copy this. So we want to consider, we can rename this to the KM1. So we want to consider a covariate when drawing our so which of the covariates should we consider? Let's consider tumor stage. Let's consider tumor stage because we have stage 1, stage 2, and stage 3 in our data. So let's run that. Oh, Sorry about that. It's not running because of this comma that is there. That is why it did not run, because of the comma that is there. So, and here, you have to, this is where the comma is supposed to be. So let's run it. It ran. So we can print, print, or we can just call it, instead of printing KM1, it is still going to run. See, look down here. You see, we have tumor stage 1, tumor stage 2, and tumor stage 3. And the numbers of patients from 313 that are having tumor stage 1 is what? Is 60. Numbers of patients tumor stage 2 is 177, and numbers of patients tumor stage 3 is 176. So those that are at risk, those that experienced the event, the particular event, that means those that died from the during the survey are 9, 35, and 17 respectively. So the median survival time of people, those that died at tumor stage 1 is not known because the event is not sufficient enough, it's not large enough to be calculated, and the median for those in tumor stage 2 is 35, and for tumor stage 3 is sorry, the median for tumor stage 2 is 1148 days. So the numbers of days is going to take for 50% of those that have tumor stage 2 to die is 1148 days, and likewise for tumor stage 3. We can also draw the life table when considering this particular covariate of KM1. Why is it not running? Okay, I wrote 3 M's instead of 2. So what's wrong? So this is the life table for each stage. This is for stage 3. If you move up, you are going to see for stage 2 and for stage 1. This is the life table for stage 1 and the life table for stage 2 below. So it is the same explanation to the previous one. We can go and draw. So we can draw the Kaplan-Meier curve for this, considering the covariate. We can just use plot, because plot, the graph will not be appealing to the eyes. So let's use the ggplot, the ggplot function. So you use the ggplot. So I want to do something here. I just want to make something here. I want to add a particular line of code here, because we will be working this particular code I want to add there is just, it will be doing something. P val will be equals to true. I just want to, so this p val is equals to true, and p value method. So if I run this, it's going to bring out, you see, this p value, it has done something on the ground. This p value is for the log rank test. The log graph automatically done the log. You see this red, you can see the various strata for tumor stage 1, which is this green red line. This one belongs to tumor stage 1. This is the red line. Tumor stage 2, which is the green line, and tumor stage 3, which is the blue line. But all these shades, I don't want to see this shade. Let me make the confidence interval to be false. So let me remove the shades so that it will be more. Run. So you see the shades are gone. So you can see the graph clearly. So this particular red line is talking of the survival pattern of those that had tumor that are on their tumor the first tumor stage. And this green is talking of those that are in the second tumor stage. While the blue one is talking of those that are in the third tumor stage. This step represents the time at the time of another, like, let me say the day at which a particular patient dies. So this step is just representing each of them. So this is the Kaplan-Meier curve when we are considering just one covariate. We can still do that for different covariates, different covariates in our data. So, but I will just be doing that one. So we are going to be moving to, okay, let's calculate for, this is the p-value. This is the p-value. So we are going to be p-value. If there are three different methods of doing hypothesis test, we have the traditional method, the p-value method, and the confidence interval method. But if you don't want to use this p-value, because p-value is actually, for me, I think p-value is the best method. But if you don't want to use p-value and you want to look for a calculated value for your chi-square, you can just do this. You are going to just use the Cox proportional. You can name it to be Cox 1. So equals to. So this Cox is a function in the survivor. Cox is a function in that survivor package that we installed earlier. So we have to. So you can have two arguments in this solve. Are you following? So y, our survivor time, which is what? Surgery, survivor days. So, and our status, which is what? The status 2, which is our status. Then you can use this tilde sign, the tilde sign. Then you put your, which of, okay, we are considering tumor stage. Sorry, it's not C, it's Y. Tumor stage. So let's run this. So we have done the cost proportional model considering just one variable. So we just use summary to see. Summary of Cox 1. As you can see down our results here, this is the code, the line of code we just ran, and our numbers of event is numbers of the total number sample used is 313, and the numbers of event experience is 61. This coefficient here is the coefficient of beta from that our previous this slide. That coefficient is this beta 1. The coefficient of that first, now we are dealing with just one covariate. That means this x2, x3, x4, they are not in the model. We are just dealing with one particular covariate. So that is what this one is saying. So this one, you can see we have three stages: tumor stage 1, tumor stage 2, and tumor stage 3. But in this our results, you can just see tumor stage 2 and tumor stage 3. So it has taken our tumor stage 1 to be our reference variable. It has referenced tumor stage 1. So that means tumor stage 1 will be interpreting this our result with respect to tumor stage 1. And if you take the exponential of this coefficient, you are going to get 1.5810. You can try it. The exponential of, let me just run it here. You see exponential exp. Y caps exp of these are 4 point. Let me just copy it. So when I run it, why is it bringing error for me? Why is it bringing error? Oh, I did not put my bracket. Sorry. So you can see the exponential of this is 1.58. So the exponential of this coefficient is this x coefficient of 1.58. This is the hazard ratio. This 1.5810 is our hazard ratio. So, and from our slides, I explained that you interpret your cost proportional hazard ratio with its closeness to 1. So from here, I will interpret this to be 1.5810. It means that this tumor stage 2 has 0.58 Patients that are on tumor stage 2 are 0.5810 times more likely to die than patients of tumor stage 1. Let me come back again. You see, 1.5810 is the hazard ratio. It means that what? This tumor stage 2, they are more likely to die earlier than die 0.5810 times more than patient of tumor stage 1, because we have used that tumor stage 1 to be our reference category. So we will be interpreting this with respect to tumor stage 1. So this is the standard error of the coefficients, and this Z is the Z statistics, the wild statistics, the Z wild statistics, and this probability of Z is the P value. You can see that for tumor stage 2, it is not significant, and tumor stage 3 is actually significant in explaining the survival of breast cancer patients. You can see it is less than our traditional 0.05. So, and you know, in the p-value, if the p-value is less than 0.05, we do not reject the H naught. So we move down here. This is also almost the same thing as what's up here. This lower 95% confidence. This is our lower 95% confidence interval, and this is our upper 95% confidence interval. So this concordance, you see, it is concordance. It tells how well the model predicts individual experience in time. This concordance is just telling us how well this model predicts the survival experience of patients. You can see this is 0.566 times. So it's just telling us how well it predicts the model. It's predicting the model like 56. That is like U is close. It is like what should I compare it with? Like, should I say our R squared? Should I say R squared in normal regression analysis? So this is just telling us that the model is 56. It predicts how well it predicts our model. That is 56.6%. This likelihood ratio test, the wild test, and the log rank test, they are asymptotically equivalent to each other. They are just testing the survival experience within this survival experience of stage 1, stage 2, and stage 3. And you can see this is the calculated value, and this is the if you look at this p-value, is the same with the p-value that is here. Like it's just approximated to 2 decimal places. So it's the same with the p-value that is here. And you can see if our values are really large, these three are going to be the same. The cost proportional hazard for the full model. So to draw the, sorry, let me rub this off. This is not supposed to be here. So for the cost proportional hazard for the full model, you are just going to bring the entire model, the entire covariate that you are considering, the whole covariate that you are considering for this particular study. You are just going to put them there, just like this Cox one that we did. You are going to put everything there. So we can just and this is the code for the Cox proportional hazard model. So Like the first argument there should be our survival time, which is the survival days, and our second argument should be our survival, the status of the patient. We are using status 2. So I won't be using all the covariates that is here. I won't be using all of them because there are some that I really that are not really. I've converted them already. You put your tilde sign, this tilde sign, to show that you are this tilde sign. Then you input the covariates that you are considering. Let's consider 5 of the covariates. So let's consider age, which is continuous, a continuous variable. Let's consider age. Let's consider, you use the plus sign. So let's consider another variable. Then okay, from that our data, we have just a gender in our data, which is a female. So it is only female that are there. So I don't think I should be considering female because we don't have the male in that data. So we won't be considering gender. Since I've picked one continuous variable, which is age, I won't be picking this protein 1, protein 2, protein 3, and protein 4 because they are all continuous also. So I won't be considering that because our this thing will be too large. Our model will be too large. So I will consider at least, let me say at least 5. I consider tumor stage, which is continuous. Which is a categorical data, sorry. I will consider the histology. Let's consider another, which is the ERO status there. The ERO status is, I think everything in that data is entirely positive. So I won't be considering ERO status and PRO status because they are all positive. And the ERO status is positive and the PRO status is negative. So let's consider the HERO status, which have the positive and the negative. So we consider that. Let's consider another covariate. Let me use, I think this should be the last covariate we should consider from this model. Let's consider the surgery type. Okay, let's consider the surgery type. So I can run this now. So we just look for the summary of for hazard, the cost proportional hazard model. This is how the model looks like. This is very similar to the last line of code we ran just now, which is the n numbers of the sample size, the sample size that we considered, and this 61 is the numbers of events that happened, which that is 61 of the total patients died from this survey. So you see this this coefficient, or those beta one, you can see this continuous is just writing just continuous. There are no referencing and nothing. And this exponential of the coefficient, this is the hazard ratio. The exponential of the coefficient is our hazard ratio. If you take the exponential of 0.0049, you are going to get this, which is our hazard ratio. This is just telling us that as the patient goes older, the probability that the person is more likely to 0.005 times more likely to die than a patient that is, if you are adding one a unit increase will lead to 0.0049 increase in the survival rate of patient. This just for continuous. You are not interpreting this with respect to a reference category or anything. So like I explained earlier, this is the standard error, this is the word test statistics, and this is the p-value. So you can see the tumor stage, that's tumor stage 1, tumor stage 1 is the reference category here. The histology, we have the infiltrating lobular carcinoma, we have the mucinous carcinoma, and I think one of the histology has been referenced already. So I don't know what was referenced because I did not check the data. And you look at the HER status, negative was referenced and positive is in our model. So this is just how you can okay now you see this infiltrating lobular carcinoma, you can see the hazard ratio is 0.766311. So this means that 1 minus this 0.01, this is less than 1. So it means that this infiltrating lobular carcinoma are less likely to die compared to the reference category. So it means that these one are like 1 minus this. If you do 1 minus 0. Now you are going to get 0.2, I think 24 something. So they are 0.24 something less likely to die after doing the surgery than patients that are at the reference category. So, and you can see from all this, you can see that this is the only variable that is significant to the model. You see, it is only tumor stage 3 that is significant in explaining the survival time of the model. So 0. This is only significant in explaining the model, and I think we have come to the end of the practical. So